Okay, continuing on, let's look in more detail at Earth's magnetic field. Now, we saw before that liquid iron in the outer core is stirred into convection motion by Earth's internal heat. And the circulation of liquid iron in the outer core, in turn, produces electric currents. And these electric currents are what generate Earth's magnetic field. A good analogy is the Earth's magnetic field is an electromagnet, where here we have a battery and coils connected to the battery wrap around this nail. And as current passes through the coil, the current generates a magnetic field that leaves the base of the nail, wraps around, and enters the nail again at the very top. And so, too, it's envisioned that Earth's rotation causes spiral flow in the liquid outer core, which in turn aligns with the spin axis. And the cylinders of spiraling iron behave like the coil of current passing through wires of an electromagnet. And this spiraling electrical flow, in turn, is what generates Earth's magnetic field. If you look at the magnetic poles do not coincide with the Earth's rotational axis, the geographic poles. Instead, the magnetic pole tends to vary over time with its relationship with the geographic pole. So we see that the magnetic lines of force today, at least under normal polarity conditions, exit at the magnetic south pole, and the lines of force enter the Earth again at the magnetic north pole. Magnetic lines of force parallel Earth's surface at the magnetic equator, but then, as we saw before, at higher latitudes in the northern hemisphere, the magnetic lines of force enter Earth at greater and greater angles. In other words, the inclination tends to increase as we go further north in the northern hemisphere, to the point that the lines of force enter perpendicular to the surface at the magnetic north pole. On the other hand, within the southern hemisphere, the magnetic lines of force are leaving Earth's surface. Seismic waves indicate that Earth's inner core is actually rotating faster than the rest of the planet by about 1 degree per year. And this faster rotation of the inner core may in turn play a role in the generation of Earth's magnetic field, and also influence periodic magnetic reversals, as we saw before, occur in cycles of roughly 700,000 to 1 million years. But if we look at this figure on the right, we see that the fastest route for seismic waves in passing through the inner core is gradually shifting eastward, and this is why it appears that the inner core is rotating faster than the rest of the planet. And here we see the change in the measured location of the north magnetic pole over time, from about 1904 to its present position at 2015. So this is significant wandering of the north magnetic pole in just a little over 1 century. In addition, the magnetic field has also weakened by about 10% over the last century, and the question is Earth's magnetic field in the process of undergoing a reversal? The thought comes from actual computer simulations showing how Earth's magnetic field could reverse direction. And the whole process the simulations predict that the magnetic poles are going to gradually move. And in doing so, the overall strength of the Earth's magnetic field is going to gradually weaken as the poles migrate. And eventually there's going to be a flip where we get a reversal in the direction of the magnetic lines of force. And this overall reversal is only going to take a few thousand years based on these computer simulations. And another question is, what would be the effects on life? Again, we don't know, because the last reversal was 700,000 years ago, long before recorded human history. So let's move on and look at Earth's internal heat. Earth's temperature gradually increases with depth at a rate known as a geothermal gradient. And we touched upon this before early in the semester when we looked at particularly metamorphic rocks and things of that nature. But in the figure to the right, we see the Earth's geothermal gradient represented by that black line in plots of temperature versus depth. Now, the geothermal gradient varies considerably from place to place and averages somewhere between 20 degrees and 30 degrees Celsius per kilometer depth within the crust itself. However, the rate of increase in temperature with depth is significantly less in the mantle and the core. And this is shown again in the figure to the right. Notice that within the crust, within the upper 60 to 100 kilometers of the Earth, there's an abrupt increase in temperature with depth. But then as we pass through the mantle, the increase in temperature with depth is more modest. And then when we enter the D double prime layer, there's again an abrupt increase in temperature with depth, followed by a modest increase of temperature with depth within the outer and inner core. So clearly something is changing in these different seismic layers or mechanical layers, and we're going to look at this in a little bit more detail. Now let's start at the surface, where we see partial melting within the upper asthenosphere, within, again, known as the low velocity zone. And that's because if you follow the geothermal gradient, it passes slightly into the melting field for mantle peridotite. And as a result, this tells us that the upper part of the asthenosphere consists of partial melt, something on the order of 1 to 2% liquid, 98% solid. And as we go through the mantle, through most of the remaining mantle with depth, the geotherm is well within the solid field at lower temperatures from the melting curve. And that tells us that much of the rest of the mantle, particularly the lower mantle, is solid all the way down to the boundary with the outer core. But as we pass through the D double prime layer, we again see an abrupt increase of temperature with depth. And we're going to look at this in a little bit more detail. But further down within the outer core, notice now that the geothermal gradient temperature is higher than the melting temperature of iron. The gradient is well within the melting field of iron, so this tells us that the outer core is liquid. And then when we finally enter the inner core, the geothermal gradient is again below the melting temperature of iron. Now here's a question. Why is the geothermal gradient within the melting field of iron in the outer core, but is within the solid portion at lower temperatures within the inner core? What's the distinctions between the outer core and inner core? Yeah, pressure. The difference is that the inner core is at much higher pressures than the outer core. So that even though the temperature of the inner core is even higher than that of the outer core, the greater pressures shift the geotherm into the solid region. Okay, so it's actually pressure, yeah. Major processes that have contributed to Earth's internal heat included the heat released by colliding particles during the formation of Earth back about 4.57 billion years ago. There was also the heat released as iron crystallized to form the solid inner core of early Earth. Heat emitted by radioactive decay of isotopes, and even the moon-forming impact that occurred at 4.5 billion years ago certainly added more internal heat to our planet. And if you look at this diagram here, this is Earth's temperature in the vertical scale versus time in the horizontal scale. The origin dates back to 4.567 billion years ago, where Earth's temperature was many times higher than it is today, possibly as much as 6 to 7 times higher than today. So we see that young Earth began as very, very hot planet because of the heat generated by collisions with planetesimals, and also, in addition, because of the heat released by the decay of short-lived radioactive isotopes, like, for example, 26 aluminum and so on. Now, these early short-lived radioactive isotopes only had half-lives of a few million years and have long since decayed, so that over time Earth gradually cooled. However, if the Earth's only source of internal heat was generated during its early formative period, our planet would have cooled and froze to a frozen planet long ago. However, the mantle and crust even today contains what are known as long-lived radioactive isotopes. And it's the decay of those long-lived radioactive isotopes like 238 uranium, 235 uranium, and potassium-40 that keep our planet warm within the interior even today. So Earth's internal heat engine can be considered by looking, first of all, at heat flow within the crust versus heat flow within the mantle. Now, we saw before in looking at the profiles of the geotherm that within the crust there was a significant increase in temperature with depth. And so the overall heat flow in the crust is thought to be the result of conduction, which is not a very efficient way of transferring heat from the base of the crust to the surface. Conduction is the way that heat is transferred in the handle of a pan where the water within the pot is boiling. And if you took the temperature of the handle next to the pot and the temperature of the handle at the very end where the hand is holding it, there's quite a bit of a temperature difference. And so the handle does not transfer heat very effectively, and this is basically conduction in a nutshell. On the other hand, heat flow in the mantle, there is only a modest increase in temperature with depth in the mantle as shown by that geotherm. And as a result, the mantle must have an effective method of transmitting heat from the core outward to the base of the lithosphere. And that method of heat transfer is likely convection. As, for example, the way this is also the way in which heat within the boiling water is transferred from the base of the pot to the top of the water column. In other words, when you look at water boiling on the stove, it's circulating, and that's what's known as convection. It's a very effective way of heat transfer. So let's look again at a cutaway view of the Earth, and beginning within the solid iron inner core. The inner core is solid because there the temperature of the geotherm is lower than the melting point of iron, and it's thought that conduction is the main way of heat transfer within the inner core. But then moving up into the outer core, because the outer core consists of liquid iron, heat transfer is probably a combination of both conduction and convection. Moving up into the D double prime layer, we see in the geotherm on the right an abrupt change in temperature with depth. This tells us that heat transfer within the D double prime layer is likely mainly by way of conduction. And then moving up into the mantle, we again see a modest change in temperature with depth. Convection is likely the means of heat transfer within the mantle. And then when we get into the lithosphere, again we see in the geotherm an abrupt change in temperature with depth. Heat is transferred from the base to the top of the lithosphere, mainly by way of conduction. And once Earth's internal heat reaches the surface, it is then radiated out into the atmosphere. We can actually measure heat that's being brought up to the surface using special instruments, and what is found is that Earth loses most of its heat near mid-ocean ridges where magma rises to fill the gaps formed by as tectonic plates spread apart. Continents actually emit more heat than old ocean seafloor, on the other hand, and that's simply because continents contain higher amounts of heat-producing radioactive isotopes, particularly long-lived radioactive isotopes like uranium and thorium and potassium. But these different colors just simply show heat flow in milliwatts per square meter of surface area. And basically we see that the reds and the oranges, the areas of highest heat flow, tend to coincide with mid-ocean ridges, whereas areas of low heat flow, the blues and the greens, coincide mainly with the interior of continents. We saw before that mantle convection is the main way of heat transfer within the mantle. And what we find that mantle convection is a very important process occurring in Earth's interior. It provides the force that moves rigid lithospheric plates. And because we see that mantle had transmit S waves and at the same time flows, it is referred to as exhibiting plastic or a ductile, both solid and fluid type of behavior. And hence we get mantle convection. Seismic thermography is a three-dimensional model of Earth's interior based on seismic imaging. and requires seismic records from many thousands of different earthquakes from around the world. And basically, seismic tomography identifies regions within Earth's interior where P and S waves are faster or slower than average. And these velocity variations in seismic waves are attributed to variable temperatures and other material properties within Earth's interior, such that higher temperatures equate to slower velocities, whereas lower temperatures are attributed to faster or greater velocities. So here, for an example, we have a cutaway view of Earth. The core is whited out, and so all the colors that we see, the reds, the blues, and greens, all are within the mantle. This particular cutaway view of the Earth occurs along this profile within this inset numbered 1, 2, 3, 4, 5, where the number 1 corresponds to the Pacific Ocean, the number 2 to North America, number 4 to the Mid-Atlantic Ridge, and number 5 positioned over Africa. So in other words, this is just basically a cutaway view or cross-section of the Earth. Now the reds are areas of the mantle. The reds and oranges are areas of the mantle where the velocity of S waves are slower than average, whereas the blues and the greens are areas of the mantle where the S wave velocity is faster than average. And so just looking at the tomographic image of this particular figure, we see that the western United States, for example, is very, very warm, and this is due to this region being tectonically active. And as a result, the continent being warmer and weaker slows down S waves. On the other hand, notice that in the center of this image, there's a large blue structure extending far beneath North America, is basically descending into the mantle. And this structure is likely a sheet of cold, dense, ancient Pacific oceanic lithosphere that's sinking towards the core mantle boundary. And as a result, S waves tend to speed up within that sinking lithospheric slab. On the other hand, notice that we have regions like this African superplume towards the right that's beginning at the core mantle boundary within the D double prime layer and slowly rising towards the surface. And so these large red regions beginning from the core and extending up into the mantle could be the giant megaplumes originating from the core mantle boundary. And those regions will dramatically slow down S waves because they're warmer than average mantle. But anyway, this just basically shows how temperature differences can be distinguished based on the changing velocity of S waves and P waves. And this allows us to kind of generate CAT scans of Earth's interior, and from there we make all these different interpretations based on the patterns we can see. Yeah. Whereas the continent of Africa to the very right is blue because Africa is a very old, thick, cold, rigid continent. And so seismic waves speed up when encountering the crustal rocks of Africa. Now, Earth's rotation produces a bulge at the equator and a flattening at the poles. So, for example, if we measured Earth's diameter at the equator, it would be something on the order of 12,756 kilometers, or 7,926 miles. On the other hand, if you measured the diameter from North to South Pole, it would only be 7,900 miles. There's a difference of about 26 miles from measuring from the equator versus pole to pole. And that's due to the Earth slightly bulging out at the equator due to its rotation. Now, Earth's equatorial bulge results in greater gravitational acceleration at the poles relative to the equator, and this occurs for two reasons. One, centrifugal or rotational force, which counteracts gravitational force, tends to be greater at the equator than at the poles. And the second reason is that Earth's surface is a little bit further from the center of gravity at the equator than it is at the poles. And as a result, a fisherman who weighs 200 pounds at the North Pole will only weigh 199 pounds at the equator. And there's an actual figure in your book that shows this. Now, other factors that affect Earth's gravity include elevation and density differences of rocks below Earth's surface. With respect to elevation, higher elevation puts Earth's surface a little bit further from the center of gravity, and as a result, gravity decreases slightly at higher elevations. In addition, higher density rocks below the surface will increase gravitational attraction locally. And here's an example of 3 gravity meters. And notice that the gravity meter on the left, which sits above dense metallic core, is pulled down a little bit stronger relative to the gravity meter in the center. And that's because of this dense metallic core, which exerts a greater gravitational attraction on the surface. On the other hand, the gravity meter on the right sits above an opening, a cave. So there's less gravitational attraction occurring beneath that gravity meter to the right. And as a result, it's not pulled near as much down as the other 2 examples. So this just is an illustration of how gravity changes depending upon densities of underlying material. Now here's something else interesting. A region in isostatic balance gives a uniform gravity reading after correcting from the differences in elevation. And that's shown in the lower left-hand figure. So notice that we have a mountain, and then we have 2 lowlands on both sides. And notice how much thicker the crust beneath the mountain is relative to the crust on either side of the mountain. But if we take a gravity reading above the mountain and correct for differences in elevation, we get a flat gravity reading if the region is in isostatic balance, which simply means that the balance between the mantle and the crust has been adjusted to be in equilibrium with one another. And that's about all I'm going to say about isostatic balance. Just take that. Okay. Because notice the figure in the upper right-hand corner, we have a region undergoing tectonic uplift. And as a result, we get a positive gravity anomaly where the gravity reading increases over that uplifted region. Conversely, in the lower right-hand corner, where a region is being pulled downward, we're getting a negative gravity anomaly, where the gravity reading within that sink is lower than the gravity reading on either side of that depression. So here we have a map of the United States, and all these different color regions are deviations from average of the gravity reading. So in areas of blues, areas color-coded blues and greens, the gravity readings are quite a bit more negative than the gravity readings that are color-coded reds and oranges. Let's take, for example, the negative anomalies, the blue regions in the Basin and Range Province in the western United States. These negative gravity anomalies are the result of hotter, less dense, and tectonically active crust within this region. This is a region of active rifting and volcanic activity. On the other hand, if you look at the central portion of the United States, this band of red that's labeled mid-continental rift, this narrow positive anomaly that runs down the middle of the country is the result of dense volcanic rocks that have been placed in the crust over 1 billion years ago. And then to the right, within the Appalachian Mountains, we see the negative anomalies, the blues, beneath the Appalachians, again telling us that the crust has very deep roots made up of less dense rock beneath the mountains. Now, don't worry about these details. The only point to this figure is that these gravity differences from one place to the other can be used to interpret the tectonics and the crustal characteristics of those regions. Okay, that's all I'm trying to show is basically just give you an example of how gravity anomalies and gravity variations can be used to interpret geology. That's it, okay? So don't worry about it, because I'm going to talk about the geoid, which is even more confusing. So let's start by stating that the sea level is not uniform everywhere, but tends to vary in height due to density differences of materials below Earth's surface, related to the gravity effect. The geoid is a representation. The geoid is an imaginary surface that represents sea level and is distorted relative to a perfect spheroid formed solely by Earth's rotation. So here on the right we have a mathematical model of a spheroid. And this is an exaggerated spheroid, but recall that Earth's rotation creates that equatorial bulge. That's what this spheroid to the right is representing. The shape of the Earth based solely on its rotation. And that dashed line in the mathematic model is just the trace of the spheroid representing Earth's surface. On the other hand, look at the ocean on the left and mean sea level. This is the height of the geoid at that location. And that geoid level is below the actual spheroid surface due to the gravity effect. As a matter of fact, if we plotted or drew the geoid as a red line relative to the perfect spheroid, we find that in some places the geoid pops up above the perfect spheroid. In other places, the geoid occurs below the perfect spheroid. And these undulations are mainly due to changes in the gravitational attraction at the surface due to the variable densities that are occurring below. As a matter of fact, GPS, Global Positioning Systems, measures elevation relative to the perfect spheroid, whereas traditional surveying by leveling measures elevation by way of the geoid. This example.
But theoretically, if all those other elements didn't exist, you would assume that.
Yeah, if it's strictly gravity, then the geoid is pulled down below the perfect spheroid in places where there's a greater gravitational attraction. And conversely, the geoid pops up above the perfect spheroid in places where there's less gravity. As a matter of fact, this word slide, differences in the height of the geoid relative to a perfect spheroid is caused by density differences below Earth's surface. If underground density anomalies are near the surface, geoid anomalies tend to be narrow, whereas if density anomalies are deep, the geoid anomalies tend to be very, very broad. And the reason I give you that information is because here's a map of large-scale geoid anomalies which possibly reflect underlying mantle convection. So notice that in that color-coded scale below, the 0 represents the geoid corresponding to a perfect spheroid, okay? And the reds and the oranges are places where the geoid occurs higher than the perfect spheroid. In other words, the geoid pops up above the spheroid. The blues and the greens are places where the geoid occurs below the perfect spheroid. It's pulled down below the spheroid. And so by noting the colors in this overall map of large-scale geoid, we can make several interpretations. For example, the areas of oranges and reds are possibly places where we have ascending mantle convection cells rising from the core up towards the base of the lithosphere in regions of upwelling or mantle upwelling. And conversely, the blues are places where mantle material is sinking down towards the coal mantle boundary. These are regions of downwelling. And as a result, we're basically mapping underlying large-scale mantle convection using variations in the geoid. If you look closely, you can see the outlines of the continents out as these thin black lines. For example, here's Africa to the right, and here's South America over here, and North America up here. So this is a global map.
What are some causes of mantle convection?
Mantle convection is then caused by variations in heat flow. Hotter, warmer parts of the mantle rise, cooler parts of the mantle sink, again due to density differences. There's our favorite slide. We're finished.